Okay, we're picking up here chapter 9, which is about solutions. And last time we got into really a solution. And solutions are really those sort of formulas to get the AQ symbol next to it. Means aqueous, water environment. A solution really is a homogeneous mixture, and there's two parts to a solution, as we talked about. There's the solute, which is the smaller part of the solution. And there's the solvent, which is typically the larger part of the solution. So as we talked about last time, a lot of times, again, because it is a mixture, a lot of times we take like a solid, for example, and dissolve it in something like water. So again, we had like solid sodium chloride and some of our pure water, and we put it together, we would get a sodium chloride solution. Here, the water would be the solvent, and in this case, the sodium chloride would be the solute. What allows things, as we sort of talked about as well, to sort of interact well with each other, to be soluble or mix with one another, is those intermolecular forces that we sort of touched upon. And these intermolecular forces are really the forces between two different molecules, or even two of the same molecules. And it's the force that basically holds those two molecules together. And again, it can be molecules that are the same, can be different. And these are things, for example, like hydrogen bonding, was referred to as a dipole-dipole interaction, or can be dispersion forces. And for the most part, this is also the order of the strength of those intermolecular forces. Hydrogen bonding is like the strongest, and dispersion forces are also the weakest. And hydrogen bonding and dipole-dipole are essentially the forces that typically polar molecules will use with themselves and other polar molecules. In order to hydrogen bond, you do need a hydrogen that's bonded directly to either nitrogen, oxygen, or fluorine. So those are our most electronegative sort of elements, and that will create a polar bond between those two, and you will have like a separation of charge as a positive side and negative side. So all intermolecular forces basically use those type of positive negative attraction. Dispersion forces are really the main sort of force that a nonpolar molecule will use with itself and other nonpolar molecules, are these dispersion forces. And it is the weakest of all of them. And as we talked about, what sort of makes things, again, mix with one another is this idea of like dissolves like. And what that means is, as we touched upon, I think last time, whatever sort of intermolecular force a particular molecule uses with itself, so other of the same molecules, basically, if you bring a different type of molecule in contact with that, and it's using the same type of intermolecular force that the first one uses, they will be able to interact really well together because they're both using basically the same type of forces to interact between molecules. When you bring somebody in that uses a completely different type of intermolecular force than the actual guy you're trying to dissolve it in, for example, they have no way of long-term being able to keep that interaction going. So they typically will not be able to dissolve in each other or mix or be soluble in each other. These dispersion forces, one of the major differences why they are so weak is it does require something to occur for them to temporarily gain a positive and negative side to their molecule. Because remember, nonpolar molecules are essentially neutral, no charge. So it does require, in most cases, for a dispersion force to sort of work, something to occur to allow them to temporarily gain that positive and negative attraction so that they can interact with other sort of nonpolar molecules. That is different than what happens with polar molecules. Polar molecules have a dipole moment, which means no matter what you do, for example, something like water, no matter what you do, the hydrogen side there of water is always going to be more positive, and the oxygen side there of water will always be more negative. You can do whatever you want to it. It's always has a positive side and a negative side. And that's why it's like good to go in a sense. It's got its like charges ready to interact with other things that have positive and negatives. Unlike non-polar molecules, has to rely on sort of something happening for them to sort of temporarily gain those positive and negative things. Uh, as we'll talk about as well, intermolecular forces are also responsible for like boiling, freezing points. The stronger the intermolecular forces, the higher the boiling points and melting points and freezing points. That's why, for example, a lot of organic molecules are non-polar, and they use dispersion forces, and that's why a lot of organic molecules are found like in the gas phase under normal conditions, because they're very much weakly held together. It doesn't take a lot for them to be in the gas phase. Things like methane, propane, butane, those are all sort of gases under normal conditions, and they're all non-polar as well. So when we talk about like dissolves like, we pretty much have three things that pretty much will work with that. And if you have something that's ionic and something that is polar, they are going to be soluble in each other. And that's because something is ionic or positive and negative charges, which means they got charges, and something that's polar has a positive and negative side, so they're able to interact really well. And that's how this basically occurs, where it dissolves the sodium ion and the chloride ion in solution, gets surrounded, as I might have drew last time and we saw, by the positive side of water, the negative ion, and the negative side of water with the positive ion. So that is basically ionic and polar, and that's why basically the process of dissolving something. So those interactions work really well. If you take something that's a polar molecule and a polar molecule and kind of put them together, you would expect those guys to be soluble as well. Again, because you're going to basically have this happening. Each of the polar molecules will have a positive side and negative side, which means again they're good to go. They're just gonna, arrange themselves with a positive to the negative and positive negative. They're going to be able to interact. So I think we looked at something like methanol maybe, or ethanol. And again, when you look at something like methanol here, it has this polar bond here, and that's going to allow it to work really well with something like water, which has pretty much the identical bond in it. And it's just a basic negative positive attraction between that and a water molecule. And they're going to be able to hydrogen bond with each other and be soluble in one another. Now, the one thing I might have mentioned last time as well, that sometimes people overlook when we talk about sort of solubility things and this idea of like dissolves like, and that is that you can take a non-polar thing and it will be very soluble in other non-polar things. And again, it's because they're both using dispersion forces. And that's why, again, water's a really good solvent for ionic things, for polar things, but a pretty crappy solvent for anything that's non-polar, because they will basically separate out from each other. They really won't mix. So if you had something that was like a non-polar guy and you wanted it to mix, you would need to use something other than water as, say, like your solvent, to allow it to mix something that's non-polar as well. Maybe like carbon tetrachloride, which is non-polar, and they would mix really well. So these guys will be soluble in each other as well. So really, the only sort of problematic thing is kind of when you cross over. If you take something that's polar and something that that is non-polar, they definitely will be insoluble in each other. And again, I think we might talk about a couple examples, but again, oil and water. Oil is essentially non-polar and really large, and water is obviously polar. So those guys typically do not mix. They will separate out from each other because over a long period of time, they really have no way to maintain that interaction. Kind of, again, I think I might have mentioned like the oil and vinegar salad dressing. You can mix it up and it'll mix for a bit, but eventually they're not going to be able to maintain that mixing, and everybody will sort of separate out from one another. Any question on the stuff we talked about last time there? Okay. I think this is where we left off, which was, I think we were getting to the idea of how do we know, for example, if we have an ionic compound, whether or not we would expect it to, be a solid or maybe not be a solid and be sort of soluble in each other. And we can use solubility rules to help us with this. Now, when we use solubility rules, if something is soluble, that means we would not expect a solid, and it would get the aqueous sort of symbol next to it if you were like writing an equation and the formulas and stuff like that. If something is insoluble, that means they really aren't going to mix. And if you put those ions together, you will actually get a precipitate or a solid to form, and those guys will get the S symbol. Sometimes people get confused because they're like, S seems like it should go for soluble because that's like the first letter, but it doesn't in this case. So S means solid, which means you will get a precipitate to form. So let's take a look at some of these solubility rules here. Anybody in group 1 on the periodic table, lithium, sodium, potassium, and etc. If you see an ionic compound formula and you have a group 1 guy in there, that's pretty much as far as you need to look. You don't need to look any further. It will always be soluble. And that means that these guys will get the aqueous symbol next to them. What that essentially means is they are floating around in that solution freely. The ions are basically floating around freely in that solution. If you have something that has ammonium in it, which is NH4 plus, again, there are no exceptions, which means no matter what it is, as soon as you see NH4 plus in the formula, you know that it will be soluble. And once again, it will make a solution and it will not make a solid or anything like that. Anything with nitrates, same deal. There's pretty much no exceptions. Those guys will always be aqueous no matter what the situation is. Now, if you have chlorides, bromides, or iodides in a formula, they typically will be soluble, but there are a few exceptions in this case. So if you have either chloride, bromide, or iodide, and it's hooked up with silver, lead 2, and mercury 1, or mercury 1, they would be the opposite in that case, and these guys would become insoluble. So sort of the opposite would be there, and you would expect a solid to form. If you have anybody that has sulfate in it, it will be soluble. But again, there are a few exceptions. And the few exceptions there are calcium, strontium, barium, are lead 2 sulfate. And those exceptions means that they will be solid if one of those guys are with sulfate. Now, there are some things that are typically going to be insoluble in a lot of cases in water. And if you have anything that has carbonate in it, it typically is going to be insoluble, which means it typically will have a solid. The exception is pretty much the group 1 or ammonium exception that we see up here. And if it's one of those, it's still going to be aqueous. So that is how you would work those guys. If you have phosphates, they will typically be insoluble, which means if you see something with phosphate, it typically is going to make a solid. Except the same exception there, which is basically group 1 ammonium, which means they will have and be aqueous. And lastly here, hydroxides are typically going to be insoluble, which means they typically will get the solid, except if they are hooked up with our same sort of group 1 exception, and calcium, strontium, and barium, which means that they would then be more aqueous. There are a few that are, sometimes you'll hear the word slightly soluble, and most of the times if you see something that is slightly soluble, it is considered more on the insoluble side than soluble. Everything, for example, though, does have some type of solubility. Even things that are insoluble will dissolve a little bit in reality in solution. It'll break apart a little bit. Any questions on that there? So let's see how we could use this. So for example, we took, we'll take our silver nitrate and we'll react it with a little sodium chloride and we'll make a little silver chloride. plus a little sodium nitrate. So why don't you use the solubility rules there and see what each of these will be. Give them the sort of soluble or insoluble, either aqueous or solid. Okay, so let's take a look and see again how to use this. So we'll take a look at the first guy here, which is ionic compound. It's a positive, negative guy, right? So we may not find silver on the left-hand side, but we will find nitrate, which is right there. And what we see is it is soluble in everything. There are no exceptions listed, which means this guy should be soluble. What that essentially means is when our silver nitrate goes for a swim, it's gonna break apart. And we got some silver ions floating around, and we'll have some nitrate ions basically floating around in the solution. It's basically what that means. Now, when we look here at this one, which is sodium, that is group 1, which means, frankly, you don't have to look any further than that because there are no exceptions. So I know that that is also going to be aqueous as well. I could also look at the chloride here. It is not silver, lead, or mercury with it, so it is also going to tell you it is soluble as well. What that means for our sodium chloride is when it goes for a swim, we're going to have some sodium ions and chloride ions basically flowing around. This, by the way, as you should recognize as a double displacement reactions, right? The two positive guys are going to switch partners and make two new ionic compounds on this side. Looks like I'm doing this. Now, again, we may not see silver on the left-hand side, but we do see chloride, and chloride is soluble in everything except that guy right there, which is silver, which is, in this case, what we're looking at. So because, in this case, the silver and the chloride are coming together, we would expect a solid basically to form. And lastly, here we see sodium, which means that's group 1. That's as far as we really need to look. But if you were not convinced, you could still look at nitrate, which is right there. Also, no exceptions in either of those, which means this is aqueous. So what does this mean? These are the guys you're mixing together. They're going to be floating around like that. And what's going to happen is the silver is going to go cool. I'm going to go grab that chloride, and they are going to basically precipitate out in that solution. As you see in the picture, the other two ions are just still floating around. They're what are referred to as spectator ions because spectators do what? They watch. And that's essentially what they're doing. They're just watching. The actual reaction that's taking place here is the formation of the silver chloride, or that solid, which you might remember is one of the 3 reasons why a reaction takes place is the formation of a solid. And the only 2 ions that are actually going to make it in this case is that silver and chloride coming together. Again, the other 2 are just spectator ions floating around, really just to balance out the charge, not really leading to any products being formed. Any questions on that there? Yeah. All right, I tried one, you tried one, try a couple more here. Let's go with a let's go with something. Let's go with a potassium nitrate plus a. Actually, no, let's not do that one. Let's do a different one first. Let's just split those off first. All right, we'll see that on the other side. Let's go with potassium iodide and a little lead to nitrate here. And we will make a little PBI2 plus a little KNO3, a little balancing like I'm a chemistry person here. There we go. And then let's do a little sodium carbonate plus barium nitrate. Makes a little barium carbonate plus a little sodium nitrate. We'll do the whole balancing thing because it feels right there. All right, use your solubility rules there to decide aqueous or solid for each of these guys. And frankly, that's as far as I need to go. I know that's going to be soluble in everything, so that will be aqueous. I may not see lead on the left, but I definitely see nitrate there on the left, and that also is soluble in everything, which means it's going to be aqueous. Here I have iodide, which in this case is hooked up with lead 2, which means we are going to get a solid formed here. And once again, I see potassium or nitrate. You can look at either, and they both have no exceptions, and we would expect it to be soluble here. Once again, here, what's really happening is the lead from here and the iodide from here are going to come together and make a solid. The other guys are just going to kind of float around in the solution still, not making anything. Any questions on that there? All right, here's sodium. As far as I need to look, that is group 1, soluble in everything. Nitrate, soluble in everything. Carbonate is insoluble, and we'll go with barium on that. And I'll go solid. And here's sodium and nitrate going to be soluble in this case. So same idea here. It's going to be the barium ion and the carbonate ion going to fall into each other and make a solid. The other guys are just spectator ions floating around still in solution. Any questions on how to use solubility rules? They would probably be provided for you if that's your question, and you just need to know how to use it. Yeah. Yeah. Yeah, so there's basically, you can think of it almost like having 2 columns. So the first column is either soluble or insoluble. And then if it's in the exception column, if there's something in the exception column, it would be opposite of the first one. So for example, chloride, bromide, and iodides are soluble in everything, except if it's hooked up with one of those 3 guys, the silver, the lead, or the mercury, then it switches from being soluble to insoluble. Same thing down here, for example, like hydroxide. Hydroxides are typically insoluble in everything, which means if you have OH in the formula, that's going to be a solid. But the exceptions are anybody in group 1 are calcium, strontium, and barium, for the most part, are slightly soluble. And that's why things like sodium hydroxide, potassium hydroxide are solutions. They're soluble because that's the exception. So if it's anything in here, it's going to be that. But if there is any of these exceptions, it basically becomes the opposite of the first column. Yeah. Other questions? All right. So once again, probably be provided for you. Just need to know how to use them perhaps correctly. Yeah. Okay. In some form, they'll be provided, I think. All right. Then let's talk about a couple of things. I think we might actually hit some of these things, but just in case we didn't. Again, that idea of like dissolves like. So the solubility of a solute in a solvent does depend on temperature. The higher the temperature, as we might have talked about last time, we do have a larger solubility of a solid in a liquid. Provides more energy, can allow everybody to kind of vibrate away from each other and get everybody dissolving. In a lower temperature, we have a larger solubility of a gas in a liquid. Again, at a lower temperature, we have a gas molecule in a liquid. It is moving slower, which means it's going to stay in the liquid part a lot longer before it escapes, and thus it will be basically mixed for a lot longer. Solubility gases also depends on pressure. The higher the pressure, the larger the solubility, because as Boyle told us, higher pressure means smaller volume. So smaller volume means gas molecules are much closer to each other and thus much more soluble. That's also the Diet Coke or soda can idea known as Henry's Law, right? Before we pop the top on a Coke can or whatever, under a lot of pressure, and all your CO2 is dissolved in the liquid part, right, of your soda, which is why when you pop it open, you see what coming out, the fizzing, and that's the CO2 gases escaping, because you did 2 things. You essentially released the pressure, and you also gave the CO2 molecules an escape route. That's also why when you leave your soda can out for a while and come back to it, it tastes, yeah, because all your CO2 just escaped through the hole you made right on the top of it. That's why when you have screw caps, right, they stay a lot fizzier longer, right? You prevent the CO2 from escaping, right? In a can, you pop it, it all just goes out and it escapes a lot quicker. Real life application of chemistry. There you go. All right. So there's a couple of ways we do describe solutions, by the way. When we add too much solute to solvent, a solution can be known what is saturated. And a saturated solution basically means at a given temperature, you pretty much got as much of that solid to dissolve. You pretty much hit the maximum amount that you could get to dissolve in there. So if you hit what is sometimes referred to as the saturation point, and you continue to add more solid to it, it's not going to dissolve at that particular temperature. It's just going to pile up. So again, I might have mentioned something about like a little sugar packets, right? You could get those to kind of dissolve in a cup of water. But again, if you get the Costco size sugar at some point, none of all that sugar is not going to dissolve, right? You can only get so much of it to dissolve at that particular temperature. What's the opposite case? The opposite case is what's known as an unsaturated solution. And an unsaturated solution, you have not hit the point where all that solute will dissolve. So you got plenty of room in a lot of cases. You could get more solid in this case, and it will continue to dissolve. And when you have an unsaturated solution, you continue to add solid. It will continue to dissolve until you hit a saturated solution. Yeah. So at that point, it will not dissolve anymore. And you pretty much got most of it dissolved. There's also something that is referred to as a super saturated solution. And a supersaturated solution is one where technically there is too much solid dissolved for a given amount of solvent. So how do you make a supersaturated solution? Well, frankly, you make a saturated solution. A lot of times you will heat it up. Now, because I'm heating up this solution as I'm dissolving my solid, that's going to allow me to get a lot more solid to dissolve in there than I normally would at a cooler temperature, right? Increasing in temperature will allow more solid to dissolve in a liquid. So once you do that, you can put a ton of solid in there, and then you'll have this nice solution where you have a lot of solid dissolved. Typically what you do after you heat it up is you cool it down. Once you start to cool it down, what happens to the solubility? All that stuff is in there. Starts to decrease, right? Not to mention the fact that as you're heating, you probably lost some of your water and not solvent along the way as well. So what you end up with is a solution that actually looks like a solution. It's in the liquid state, and it ends up being something that has way too much solid now dissolved in it as it cooled back down to a lower temperature. And it's a super unstable solution. It is so unstable that if you just took like a speck of whatever you dissolved in there and you dropped it into that solution, it will go, no, too much. And you will start to see all of the solid basically come out of the solution. It will go from a liquid state to a rock hard solid state because it's like a little tipping point there. You now have way too much dissolved for that colder temperature. To be truthfully honest with you, I do this experiment at other schools. It is so unstable that frankly, sometimes you just kind of put the flask down and it will just do it by itself without adding anything. So you like knock it too hard or move it too fast, it's that unstable that you'll go from like liquid to solid like almost instantly. And you can see all the solid basically coming out in solution. So most of the time we deal with unsaturated, saturated solutions. So again, saturated solution, you hit the maximum amount of solid that will dissolve. Unsaturated solution, you're not at that point yet. So you could continue to dissolve more solid. Any questions on that there? Yeah. So it does. Yeah, so normally most things when you look at tables is usually 25 degrees Celsius. But when we talk about solubility and stuff like that, you may see some tables in your book, and it does depend on the substances you're dealing with as to based on the temperature how much you could get dissolved. So a lot of times, for example, you might see like a table, and I'm totally making these things up, but you might think on a table where it's like, hey, you could take in 100 grams of water at 25 degrees, you could dissolve like 100 grams of sodium chloride or something. But at 50 degrees Celsius, you could dissolve like 200 grams of sodium chloride. So it is depending on the substance and the temperature. So sometimes you will see sort of tables like that where it'll give you like, okay, this is how much at this temperature you could dissolve in like 100 grams of water or something like that. And it will vary depending on the substance. Now, other questions? All right. All right, so a couple other ways to describe solutions. There's concentrated. Concentrated solution has a relatively large amount of solute to solvent. And by the way, when we do reactions with solutions, it is the solute that's floating around in there that is the thing that's reacting. So it's really that solute that's in the solution. It's not the solvent. It's really just the solute part that's typically like the ions floating around that will be reacting. Now we can have a dilute solution, which is a solution that contains a relatively small amount of solute. I go with the classic example of you get the giant fountain drink there before class, right? With all the ice. You leave it in your car, you go to class, right? You come back out, all the ice is melted. Yes, in your drink. You drink it because you're thirsty, right? And go, how bad could it be? And then you drink it and go, well, I think that's how bad it could be, really, when you do that. It doesn't taste the same, right? Because in between, all that ice melted and now diluted it with a lot more water, right? So you have a lot more water than you do your syrup and all that stuff that was in there originally along the way. Also, probably lost a little bit of the carbonation as well, sitting there in those plastic cups. So, concentrated solutions is sometimes referred to as stock solutions. They're, again, the more concentrated solutions. Most of the stuff that you use in the laboratory are dilute solutions. So they take those stronger solutions basically and dilute it back down. So let's talk a little bit about electrolytes. Electrolytes are substances that will dissolve in water and create ions. And it is the presence of these ions basically will allow it to conduct electricity. Now, there's a few different types of electrolytes. There are strong electrolytes, and strong electrolytes will 100%, when they go for a swim, break apart. So they will 100% break apart into ions. Most organic, most organic. No, that's not the right word there. Most ionic compounds. That's the word I'm searching for. Most ionic compounds that make a solution are strong electrolytes. For example, if we did have a sodium chloride solution, 100% of what you would have in that beaker are sodium ions and chloride ions floating around. 100%. You'll have none of these in the actual solution at that point. They will completely break apart. Nobody will stay together. And it will conduct electricity really well. So for example, if you take a light bulb that's hooked up with some electrodes and you stick it into a strong electrolyte, your light bulb will shine very brightly. So your light bulb will go off very, very brightly. It will start to shine, which I think you might be doing this week or demonstrated this week. So if you have a light bulb, some electrodes, and you put it into a strong electrolyte, because of all those ions that are there, it's going to basically make that light bulb shine really, really brightly. That, by the way, is how you know it's a strong electrolyte. If you have something like hydrochloric acid, which is a strong acid in solution, it also will 100% break apart into a hydrogen ion and chloride ion. And once again, you will have none of these still present. So again, if you took that same sort of apparatus with the light bulb and you stuck the electrodes there into your hydrochloric acid solution, it again will shine very, very brightly because it's going to be able to conduct electricity really, really well. There are weak electrolytes, and weak electrolytes will also dissolve they will dissolve in solution, but mainly stay together. So that is very different than a strong electrolyte. So if you have a weak electrolyte, for example, a lot of weak electrolytes are weak acids, weak bases. A weak acid like hydrofluoric acid. When it goes for a swim, it will break apart into an H plus and an F minus. The difference here is in the case of hydrofluoric acid, you'll get a little of these guys in the solution, but you will mainly have this guy still together. So unlike the other guys above, where you have nobody on the left still there, in this case, you mainly have that guy still together, but still produces a little bit of ions. Because it's still able to produce a little bit of ions, it will conduct electricity. Nowhere near what a strong electrolyte will do. So if you take that light bulb example and you stick it into a weak electrolyte, it will look very dim, your light bulb. So like almost like it's dying, but it'll still kind of try to light up a little bit, but it'll be very, very dim, which by the way, that is how you know that is a weak electrolyte when you see the light bulb do that. Also, if you see it in an equation, there are some different arrows that we see typically with weak electrolytes. We see these arrows that head in both directions. These arrows indicate a reversible reaction. And in a reversible reaction, we have what is sometimes referred to as the forward direction, which means the reactants will go to products. And in a reversible reaction like this, at some point, you will build up enough products that those products will decide we would like to go back the other way. And you will get some of those products then heading back in the other direction, which is what is referred to as the reverse direction. And eventually it'll reach what is referred to as chemical equilibrium. And by the way, chemical equilibrium does not mean equal. It actually has nothing to do with the amount that you have on both sides of the arrow. It means that at the point when you reach chemical equilibrium, the rate of the forward direction will equal the rate of the reverse direction. So just as quick as it goes to products, those guys will come back the other way. What that does is, because it's going back and forth at the exact same rate, is when it reaches equilibrium, everybody on both sides of the arrow just lock themselves in place in terms of how much concentration they have. They just basically stay the same, because as soon as they lose a little, it comes right back. It loses a little, it comes right back. So it doesn't mean they have equal amounts on both sides of the arrow. It just means, when it reaches equilibrium, boom, everybody locks into place in terms of their concentrations, and they will be able to maintain that forever unless you do something to screw it up, and then it'll kind of mess it up a little bit. So most weak electrolytes, again, by the way, if you have the equation, double arrows, weak electrolyte, single arrows, probably strong electrolyte. If you, most weak electrolytes, as I mentioned, are weak acids. So if we think about strong acids, there's sort of a list of 6 strong acids, which we might have talked about previously. If not, hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydriodic acid. This is like a list of 6 strong acids. The reason I put it up there is if you come across something that's like an acid, it's not one of those 6. It's probably a pretty safe bet for you to assume that it's a weak acid and also a weak electrolyte. So you could kind of just look at this list and go, okay, it's not one of those. So it will definitely fall in the weak electrolyte, weak acid range. Or if it is one of those, then it's going to fall in the strong electrolyte, strong acid range as well. Also, strong bases like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium, and barium hydroxide. They're also strong bases, and they are also strong electrolytes as well. So something like sodium hydroxide, when it goes for a swim, will completely break apart into sodium ions and hydroxide ions. That's all you'll have in that solution. And that's really why it's a strong base, because it will produce a lot of OH minus really, really fast. That's also why HCl is a strong acid, because it's able to produce a lot of free H plus really, really fast. It just has to go for a swim, and it will produce a lot of H plus really, really quickly. HF is a weak acid because in solution, you pretty much have this guy and a little bit of this guy. So although it still produces some H plus, which is why it's still considered an acid, but nowhere near the amount of H plus as something like HCl would produce. Any question on those 2 there? The last sort of electrolyte is a non-electrolyte. And a non-electrolyte will dissolve in water, but will not produce any ions. So, if you take something like sugar, which is basically carbons, hydrogens, and oxygens, which means they're going to be covalently bonded together, sharing electrons, and you threw it in some water, you will get sugar that will dissolve because it has all those OH groups on it. But because it's covalently bonded, you will get no ions, which means because there's no ions present, that is really necessary to conduct electricity. It will not conduct electricity. So if you take your light bulb, for example that we were talking about, and you put it into your non-electrolyte, it will stay off. So it will not light up at all. And again, that would be how you know it's a non-electrolyte, right? You stick it in there and basically the light bulb doesn't go off. Any questions on those three there? By the way, water by itself, is it a good conductor of electricity or a bad conductor of electricity? Is a really bad conductor of electricity pure water, because pure water is just a pure substance. There's no ions floating around. Just so we're clear, the water comes out of your pipes like in your shower is definitely not pure water. They put ions in there to purify it, so it has a lot of ions in there. Again, why you don't blow dry your hair and shower at the same time, because you'll get electrocuted very easily. Again, do not do that, which to make that clear there in the recording. But technically speaking, if you take just pure water, which I think they might even do in this experiment, it should not conduct electricity. By the way, if I had solid sodium chloride, will it conduct electricity? It will not, because those ions are stuck together. They need to be kind of floating around in the solution to do that. So they kind of has to be in their aqueous form. And by the way, just in case you're not sure, that is where you find ions in aqueous form floating around in solutions. Is pretty much where you find things with charges and ions. That's where they are basically found in solutions. So, any questions on electrolytes there? Here's the example, which I'm pretty sure they haven't updated it. It's a really scary looking light bulb here years ago, and like these electrodes, like, oh, everybody's gonna get electrocuted on that. But here's our sodium chloride, strong electrolyte. Again, they kind of go to the opposite poles, helps conduct electricity really well. Light bulb, very bright. Here are weak electrolyte. You can see a lot of the HF still together, and a little bit of those ions, so still able to conduct electricity, but again, nowhere near like our sodium chloride, where we have none of those sodium chloride units still together, and it's very, very bright. And here's our sugar. Again, no ions there. Our light bulb, again, not going off in this case. So again, strong electrolytes and non-electrolytes will typically have one-way arrows. Yeah. And again, weak electrolytes will have those two-way arrows. Yeah. All right. The next thing we're going to talk about then are equivalents. And equivalents are oftentimes sort of a unit that's used for solutions like IV bags, for example. And a lot of times IV bags are sort of measured in equivalents per liter, for example. So an equivalent is the amount of ion that is equal to 1 mole of positive or negative electrical charge. So for example, an extra N in there, it looks like. It is really based off of the charge. And we oftentimes will use equivalents as like conversion factors. So for example, if I have a sodium ion, the charge on sodium here is, yeah, and it's actually in the case of equivalence, the number is actually the most important. It doesn't really matter if it's positive or negative. The number here is 1, which means we could use it as a conversion factor and say in 1 mole of sodium ions, there is 1 equivalent. So we could basically, and it's just based on the number of the charge. And it, again, doesn't matter if it's positive or negative. So if I had a Br minus, and 1 mole of Br minus, I would have also one equivalent. So positive, negative. In the case of equivalence, really doesn't matter. It's actually the numbers, actually the most important thing here. And these are really equivalent. And you could write two conversion factors for each of these. And if you had something, say, like sulfate, right? And 1 mole of sulfate, how many equivalents should I have? Should have two. Again, it doesn't matter if it's positive or negative here. And again, we can use that as really a conversion factor. 1 mole of sulfate gives us two equivalents. Our two equivalents is 1 mole of sulfate. Now, I would say there's two sort of common units that are used for sort of like IV bags and equivalent sort of concentration, and that is equivalents per liter or milli equivalents per liter, right? So that's a milli conversion, just like in 1 liter, there would be 1,000 milliliters, right? So in one equivalent, how many milli equivalents would there be? 1,000 milli equivalents, right? So it basically works kind of the same idea as that conversion as well. So how would we use this? So for example, let's say we had a solution that was, I don't know, we'll do 0.2, maybe I'll go one more zero, 0.0250 moles per liter of sodium sulfate. So let's just say this was the concentration of this. As we will talk about in a little bit, moles per liter, and we'll just jump the gun here a little bit, is a very common unit of concentration, which is known as molarity, or big M, and that is molarity. And it is moles of solute per liter of solution. So really what we're looking at is, you oftentimes maybe see on the bag 0.025 moles per liter sodium sulfate, or 0.025 big M. You might also, this is equivalent to 0.0250 big M sodium sulfate. So those two are basically the same number. As we'll talk about when we officially get to molarity, I highly recommend not using the big M and using both units so you could actually see both of the units, which is really important. So why is this a little bit important? We're going to talk a little bit about molarity here just to tie it in with this type of calculation that we want to do. When we have something like sodium sulfate, by the way, sodium sulfate will be soluble or insoluble? It is, right? Because it's a solution and it has sodium, right? So that's all you have to worry about. So really, when we have sodium sulfate, right, in a solution, we actually have two sodium ions floating around, right? And one sulfate ion, right? That's what the two means. You have two of the sodiums, right? And only one of the sulfate. So that's really what we have floating around in the solution. So when we look at the concentration of the whole thing here, which is 0.0250 moles per liter, we could actually get the concentration of each of the individual ions here. And we do it just like we do stoichiometry, basically, right? So for every one of the whole things, how many sodium ions do I get? 2. So basically, you multiply that concentration by 2, and that will tell you the concentration of the sodium ions floating around. So if we did that, it would basically be 2 times 0.0250 moles per liter. 0.025 times 2.05. And that is going to give us 0.05 moles per liter. And that is basically our concentration of our sodium ions that are floating around in the solution. When I look at the sulfate, for every one of the whole thing, how many sulfate ions do I get? 1. Yeah, it's a 1-to-1 relationship, which means I will multiply that concentration on the left there by 1 and end up with the exact same number, right? So if I multiply that by 1, which is the coefficient, running out of room there, so let's squeeze it there. We will end up with 0.025 moles per liter of the sulfate ions. Again, it's a 2-for-1 deal, right? So for every one of those that go for a swim, you get twice as much, right? Sodium ions as you do sulfate. So the concentration of sodium ions in that solution is twice that of the sulfates. And that's what we see with the numbers. Any questions on that there? Okay, so now that we have the concentration of each of the ions that are floating around in that solution, let's say we wanted to take these guys to equivalents per liter, and we'll do both milliequivalents per liter. So we want to kind of convert them from molarity basically to equivalents per liter and milliequivalents per liter. So we're going to start with the sodium first. So we're going to start with the concentration of the sodium ion. And basically what we're going to do is just look at it like a conversion problem, right? So I'm going to start with the units for and the concentration number here for our sodium. And we're going to treat it like a normal conversion factor, which means I can keep my units where they need to be, top and bottom, right? All right, the first thing I want to do is basically need to convert the top moles to equivalents, right? What about the bottom? Do I need to do anything? I don't. At the bottom's already in liters. So I really only have to convert the top part here, right? And this is where that conversion factor that we talked about based on the charge is going to come into play. So once again, a sodium ion, as we saw on the previous page, for every 1 mole of sodium ion, we get how many equivalents? 1 equivalence. And again, based on the number of the charge. So we're going to use that as our conversion factor to go from moles per liter to equivalents per liter. And it's just like a normal conversion, which means I want to get rid of moles, which means moles should go on top or bottom. Bottom. So on the bottom should go 1 mole of sodium, and on top should go 1 equivalent of sodium ions. The moles will cancel, and I will end up with 0.05, not moles, because I just got rid of that. So it was not write it again, I suppose. That would probably be good. Let's go with the unit I'm left with, which is equivalents on top per liter of sodium ion. Any question on that there? Now, if I wanted milliequivalents per liter, all I have to do is convert the top from equivalents to milliequivalents, right? So if I take the top guy that we just got, and as we saw on the previous page, in 1 equivalent, there are 1,000 milliequivalents, right? Where we talked about milliliters and liters, basically. On the bottom should go 1 equivalent, right? On top should go 1,000 milliequivalents. Those will cancel, and we'll take our 0.05 times it by 1,000. And we're going to get 50 milliequivalents per liter of sodium ion. So these are really just another sort of unit like molarity of the ions that are floating around in solution. And these are, again, 2 very common units, equivalents per liter and milliequivalents per liter. Any question on that there? All right, we could also do the same thing for our solution here that also contains sulfate, right? So we're going to do the same calculation for sulfate. So we're going to start with the concentration of sulfate that we started with, which is right here. And in this case, though, for our sulfate, we have 0.025 moles per liter of sulfate. And as we saw on the previous page there, 1 mole of sulfate, right, will give us 2 equivalents, right, based off of the number there from the charge. And again, we're going to use that as a conversion factor. So just like in the top one, we want to get rid of moles. So the moles need to go on the bottom here. So 1 mole of sulfate will give us 2 equivalents in this case. So the moles will cancel, And that's going to give me 0.05 equivalents per liter of sulfate. And if I take that same guy and convert it into milli equivalents here, using our conversion of 1 equivalent is 1,000 milli equivalents, I will end up with 50 milli equivalents per liter of sulfate. And that would be the concentration here of our sulfate in the solution. Are they the same number or different between the sodium and the sulfate? They're the same. And that is because when we put an ionic compound together, we need to do what with the charge? We balance it to 0, right? We balance it to the simplest way to get to 0, which means when we take a concentration unit that takes into account the charge, although we have different proportions of each of those, like 2-for-1 proportion, and based on the charge that's floating around that solution, we actually have the same charge concentration for each of those. And they should always end up the same, the cation and the anion, if you calculate these concentrations for those ions in solution in equivalents per liter and milli equivalents per liter. And that's because we balance out the charge of those ions when we put them together to make an ionic compound. So when they go floating into solution, the reason why, again, we need 2 of the sodiums per 1 of the sulfate is we need 2 to balance out the -2 charge. And that's sort of what this concentration unit tells you is sort of the balanced electrical charge concentration of those ions floating around in the solution. So that's one way you can check these type of calculations to make sure you did it correct. Is if you have a solution like that, the positive ion and the negative ion should always end up being the same equivalents per liter concentration, and also milli equivalents per liter, as you can see there, as well as the same. Any questions on that there? All right, well, I tried one. Why don't you try one? Let me just make up some numbers here. Let's go with, we got a 0.0375 molar potassium phosphate solution. And we want to know what is the equivalence per liter of the potassium ion and the equivalence per liter of the phosphate ion. And why don't we also do milli equivalents per liter for both of them as well? And again, since we haven't officially talked about molarity, once again, this is the same as saying 0.0375 moles per liter of K3PO4. All right, take a few minutes there, figure it out. I'll do it as well since I made up the numbers. Hopefully we'll end up the same spot. Okay, so let's take a look and see. So the first thing really in this situation, since you're looking really for these concentrations of each of these ions, we want to make sure that we do get the starting concentration of each of the ions correctly first. So really, you just want to think about how this thing is going to break apart. Once again, we do know it's a solution, which means it should break apart. Should be a strong electrolyte, and we know it has potassium, which means it's soluble pretty much in everything. It will give you not 1, but 3 potassium ions floating around for every 1 phosphate ion in this particular case. So that is how, when that 1 unit of it goes into the solution, basically how it breaks apart. It's like a 3-for-1 type deal with our potassium. Now, again, in terms of how that relates sort of to the concentration of the whole thing, which is 0.0375 moles per liter, you could just think about it like stoichiometry. It is a 1-to-3 relationship in terms of the potassium, which means essentially we need to multiply the concentration of the whole thing by 3 to give us the concentration of the potassium ions that are floating in there. So we'll have 3 times our 0.0375 moles per liter. And that will get us 0.0375 times 3. That will give us an arrow if you don't put 3. There we go. Try that again. And that will give us something like 0.113. I'll just round it there, moles per liter. And this will basically be our concentration of the sodium ions that are floating around again in that solution. Now, if we look at the phosphate, it is a 1-to-1 relationship between them, which means in order to get the concentration of the phosphate ions that are floating around, we're just going to basically multiply it by 1, which basically means it stays the same. So essentially 1 times that concentration. And that will give us 0.0375 moles per liter of our phosphate. Yeah. Any questions on how to get those? Yeah. It's kind of like stoichiometry where we take the coefficient in front, and we could kind of do the same thing with ions and the whole compound. So it's a 1-to-1 relationship. Yeah, and then this guy is a 1, 2, 3. So basically, when this goes in right to that beaker, for every one of those that goes in, you get 3 potassiums, right? For every 1 phosphate ion that's floating around. So that's like the 3-for-1 type deal. And again, basically what it means is it is 3 times as concentrated, right? The potassium as it is the phosphate in this case. Yeah. And that's what we see when we actually adjust the numbers. This is basically 3 times over here. Yeah. A little more with some rounding I did, but basically 3. Yeah. Other questions on that? All right. Now that we got the concentrations of each of these ions that we are looking for, we are ready now to convert it into our units. And this is where the actual formula, right, of each of the ions are going to help us do that. So we'll start with our potassium here. And from the formula of potassium, for every 1 mole of potassium ions, how many equivalents do I get? 1 equivalent, right? Because the charge here is basically 1. And if we do it for our phosphate, for every 1 mole of phosphate, how many equivalents do I get? I do get 3 equivalents. And once again, that is the number. Doesn't matter if it's positive or negative. It's again just a number in this case is the most important thing. So again, we're going to really use those as conversion factors to go from moles per liter to equivalents per liter. So let us then do our potassium first, maybe. So we'll take our little bit of rounding potassium number here. And once again, we do want to get rid of moles. So we're going to put the moles of potassium on the bottom and 1 equivalent up on top. The moles will cancel, and that will give us 0.113 equivalents per liter. As again, we don't really need to do anything with the bottom because it's already in liters, so we're good to go. By the way, if it happened to be milliliters, you might need to do a conversion, but usually they're in liters, so usually you're okay. And this would be our potassium ion, which once again, just like we used before, there are 1,000 milliequivalents in an equivalent, right? So we could use that to sort of get the next units, and that would be this conversion, and 1,000 milliequivalents up on top and equivalent on the bottom, so that those cancel. I'm not going to cancel it since we want that as an answer, but they will cancel. And that's going to get us there 113, if I am not mistaken. Again, on the round. On your calculator, you do get 112.5. So I just did a little rounding there to 113 milliequivalents per liter for our potassium. Any question on the potassium calculation there? Yes. I ended up asking for both here. So just because I did ask for both. Yeah. I originally asked for just one, then I changed my mind and said, we'll just do both. But yeah. Other questions? Yeah. All right, then we're just going to do our same calculation here for our phosphate. By the way, we already know the phosphate should end up at the exact same numbers. Yeah, they should end up at the exact same numbers. So let's just make sure. By the way, you do need to show the calculation regardless. Yeah, so we're going to go 0.0375 moles per liter of our phosphate. We're going to use our equivalents that we got up here for our phosphate, and that is going to give us 3 equivalents of phosphate per liter, not per liter, per mole of phosphate. The moles will cancel. And again, we're going to get 0.0375 times 3. That's going to give us 0.113. I'm going to round like I did on the top one there. And again, on your calculator, you get 0.1125 on your calculator there. And that is our phosphate. And once again, here we could take it to our milliequivalents per liter. And gives us 113 milliequivalents per liter of phosphate. So once again, as I mentioned before, always in these 2 units of concentration, because they're based on the electrical charge, they always should equal each other if it is a balanced ionic compound solution, which is usually what you're calculating. So that's a good way to check yourself. You didn't screw up somewhere along the way. You get 2 different numbers for the positive and negative guys. Something not right. Yeah. Hopefully just one of the numbers are not right. Yeah. And I guess if that is the case, think about the adjustment you have to do here. Yeah. And that's usually where, sometimes people will mess up on. Question on equivalents, milliequivalents. And again, pretty much that's what we're going to use them for in most cases as sort of a conversion factor. And as we saw here and from this table as well, again, doesn't matter what it is. Doesn't matter if it's positive or negative. In the case of equivalence and sort of using it as a conversion factor, in this case, it's actually the number that is the most important thing. Any questions on that there? All right, then let's talk about some other more common units of concentration. So the first one we're going to talk about is mass percent. It is sometimes referred to as mass percent. Or percent mass m/m. And it is the mass of the solute divided by the mass of the solution times 100%. Now, especially in mass percent problems, the bottom part is really important because as we've talked about here, the solution is made up of 2 things. It is made up of the solute and the solvent. So it's really important, like it shows here, that you actually get the mass of both of those things. Now, the reason I say it's really important is probably in these problems, more so than other problems, they will give you those numbers separate. So they'll give you like the mass of the solute separate from the mass of the solvent. And it's a very common mistake that people make is they just use the mass of the solvent rather than the mass of the solution. So you got to, in most cases, do a little addition here. What does that mean? This is basically grams divided by grams times 100. If you had a 4.5% mass to mass solution of sodium chloride, and you wanted to use that in a calculation, and you want to kind of turn it into a conversion factor, the easy way to do that is when you have a percentage is assume you have 100 of something, right? And bless you. And that's because when you do that, it will keep the numbers the same. So the numbers won't change. So that makes it a little bit easier. So basically, if we did that and we want to kind of use this in a calculation, you could actually turn this into 2 conversion factors. This basically means that you have 4.5 grams of sodium chloride in 100 grams of solution. You could also use it in the opposite way if you needed to. I'll write it over here. In 100 grams of the solution, you would have 4.5 grams of sodium chloride. So sometimes in problems, they'll give you like the percent mass to mass. And a lot of times it's kind of easier to do it more like a dimensional analysis problem and a conversion factor problem, just kind of get rid of the units you don't need and use it as a conversion factor. You obviously could also just plug and chug into the equation as well. So let's take a look at one maybe here and see what you come up with. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams. Calculate the mass percent of. Okay, let's take a look at it. So we're obviously calculating our percent mass to mass, and that's going to be our mass of the solute divided by the mass of the solution times 100%. In this case, the calcium chloride here is going to be our solute, as that is the smaller number, right? Larger part there is going to be our water, right, which is our solvent. So our mass of the solute in this case is going to be 2.5 grams. The mass of the solvent will be 50 grams. That means we do need to add these together to get the mass of the solution, which would be our 50 plus our 2.5 grams. Going to give us 50 point or 52 maybe. 52.5 grams in this case. Slow down, there we go. All right. All right, now that we have the right numbers, again, we do not want to use just the 50 in this case. So we can pop it in here, percent m/m, going to be our 2.5 grams divided by our 52.5 grams times 100%. And that's going to give us 4.76%. And you can leave it usually m/m. And you can put like calcium chloride here, since that was the solution we were dealing with in this case. Any questions? So again, very common mistake. People just multiply by the 50 here, the solvent, not the solution. Any questions on that one there?